Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. We are in the module number 6, the week 6, and this is the 28th lecture in serial. And the lecture topic of today's half an hour will be on the shell structure. So, we will start this particular lecture with these 4 conceptual points. We will cover that one after another. So, we will start with the introduction and the example and the development of the shell, and we will also discuss about the stresses in the shell structure. Then we will see the what are the structural advantage of the shell, and finally, we will going to classify the classification of the shell we will discuss. As you know, this is shell is a one type of the form active kind of structural systems, and it is a derivative of arch, and definitely the arch action will be come into account. So, we will initially discuss, or our learning objective in other way around will be the outline the behavior of the shell, structural behavior of the shell, and at the end we will what we will do by doing so, we have to classify the different type of shell with some illustration. So, the thin curved surface member is called as a shell, and which is very much useful for covering the roof, and also it acting as a structural systems also. So, shell is typically of found in nature. There are a lot of examples in the nature that they are actually getting protected by the shell, and also you will see the lot of the classical and modern architecture also through the shells and all, and there are some of the things that people has developed is also shell. So, if you see some nature examples on the nature, there are 2 right hand side and the left hand side there are 2 figures. The shells are of nature, and the central figure, as you all know, that is the aeroplane, which is a kind of a shell, because it is covered with a thin curved surface and experience a lot of load because of the aerodynamics comes into the play in when a particular aircraft is moving. There are a lot of examples in the shell. I have given you 3 examples or 2 such examples, but there are a lot of engineering application of the shell, and this egg I have discussed in the last lecture is a shell of by its nature, which is a natural kind of a shell. Even sometimes we get experience to shell structure from the eggs and how it is going to behave. We have talked that it is very strong if you want to break it from the top, and it is very weak if it is push it from the below. So, that is we get some of the information or some knowledge from this in nature. So, pressure vessels are also shell. There are a lot of air pressures under it, or maybe some kind of a fluid pressure which can be held by virtue of shell, and it can be economized by the shell or kind of a curved profile, and because of that there are a lot of saving of material. There are silos where we can store some grains, cement and all are of cylindrical shell in nature. There are nuclear reactor which is hyperbolic kind of a shell, and which are absolutely interesting or very aesthetically beautiful to see, but this had some kind of a structural advantage also to maintain that kind of the shell. Why it is something like a hyperbolic kind of a thing? It has enormous height, and that can be taken by its grounded by virtue of its own surface through that particular profile. The cart tire is also a kind of a torus, kind of a shell structure also. So, it experiences lot of huge amount of air pressure inside, and that can be taken into account by virtue of the curve profile also. And last but not the least, don't be afraid, this is also a shell structure, the human skull our skull is a kind of a shell, and this bone is a, it is a brittle material. So, somebody hammering my head or something like that, it cannot be disturbed by the brain, cannot be disturbed the brain, because of this is in the nature of the shell, and that will going to protect the brain from the outside attack, something like that, right. So, those are the typical example of the shell. And now, let us see how the derivatives of shell comes from where, who is its ancestor or something like that from the structural point of view. If you see the one dimensional case, beam, if you go to the beam, and if you go to the beam, and then it is a straight line, or this kind of a beam is a straight object or the straight line, and if you make it two dimensional, if you make it a slice of beam or series of beam, or if you just drag a beam, you get a plate which is a flat surface. Whereas, if there is a arch which is a curved line, and if you drag it, if you drag a this kind of a arch throughout, you will get a shell, and which is a curved surface. So, this is the derivative of the shell and the arch, or the shell and the beam, beam and the plate, and the arch and the shell from that particular point of view. So, a curved two dimensional structure is called shell. Now, the stresses in the shell, how it will going to affect the stress, and how it will going to have the different type of stress. As we all know, the curvilinear profile produces compressive stress, but it also create a membrane compressive stress, it will create for the arch, because arch is a linear material. So, when you make it a linear material to a the two dimensional material, it will experience some other stresses also. It will experience tensile stress, it will experience compressive stress, also shear stress. But out of these three, the compressive stress has a major role to play, or it is maximized portion will be under the compressive stress. We will finally discuss the amount of stress and all when we will go to the next chapter, when we will discuss the dome. And as it is stresses are applicable to this membrane of the shell, that is called the membrane surface or the membrane stress. This kind of a membrane stress will going to create. So, it has to be transferred those kind of stresses and through its membrane surface also. And in the if its efficiently is based on the curvature. So, how it is curved? Is it curved in a simple circular manner? Is it a parabolic, or it is hyperbolic? So, those are different type of the shapes will give you the efficiency how this particular membrane stress has been taken care of. So, maybe some of the profile gives you almost everything compressive, some profile may give you almost 80% compressive and 20% tensile, something like that. And also it will allow a alternate stress path. Suppose there is a shell and there is some problem in the sense there is some kind of a structural disbalance or something like that, because of some kind of a differential settlement or whatever. So, it will give you a alternate stress path, that is also very important, as and when we see any kind of a structural systems which is can be disturbed because of some kind of a wind or maybe cyclone or maybe earthquake or something like that. So, shell also has a advantage in that. And also now let us come to the material point of view. It is the shell can be constructed in lot of material. It can be constructed by metal, glass fibers, plastics and the plywoods and all, but the reinforced concrete shell is it's very popular. It's can be constructed, and it's because of it is monolithic in nature, it can actually distribute the membrane stresses in a beautiful way in its own the surface or so, and can be effectively used as a wonderful material for the shell by reducing its thickness and all, and we can have a wonderful long span structural systems with a very minimum amount of thickness of the roof or so, which going to give us a saving of lot of material also. So, as I understand or as we discuss that a membrane stress will be experienced by the shell, which shell will exhibit that. To resist that particular thickness you require some kind of a bending moments or those external force creating the bending moment, you require the thickness to take care of that particular moment. And the membrane stresses is compared to the forces that are tangent to the surface will going to define the particular shell, and the equivalent axial component axial stress is also comes as a arch in kind of a arch, and thickness of the shell is designed based on the development of the membrane stresses and the materials and all those capacities of the materials also. Okay. So, those are the some of the things has to be taken care of. So, now if you experience the membrane stresses, it will be understand from virtue of this kind of experience. Suppose it is a hanging kind of a bag. If you put some load and this you will see this particular change of pattern of this particular weave threads or this ropes by virtue of any rope or by any load or some garden chair. By virtue of that this portion is stretched, this portion is not that much stretched. Okay. So, that will give you a beautifully that how this particular membrane stress is changing in its behavior by virtue of this elongation and contraction of this particular thing. So, wherever there is elongation there is a tensile thing, wherever there is a compressive things those are the short it is very densified, but this is you remember this is a case of a arch. So, I am sorry, this is a case of a cable, but the shell is a invert of that particular cable. So, if you feel like look like these portions the maximum portions is under going to be a tensile because it is elongated, this is very much illustrated kind of a thing or stretched kind of a thing. If you reverse the action and put the load from the top, it will have a reverse action in case of the shell. It will be much compressed most of the portion and some of the portion, though this portion will be now experience some kind of the elongations also. So, we can experience those membrane stresses by virtue of the how it is loaded and how it is going to be the shape formations also. This is a particular arch which is a definitely it is a machinery kind of a arch which is a Kisra or the great arch is in Iraq. If you see the thicknesses of the arch, in the top the thickness is small, but it increase at the support. That means, the variable thickness of the shell is actually to encounter the membrane stress. The membrane stress you will experience in this zone and membrane stress you will experience in this zone will be entire has a difference. So, it is membrane stress at the crown point will be little less with compared to the near to the support, and also you know at the near to the support there are thrust which come into the action, and the amount of horizontal thrust is getting higher as and when it is come to the near to the support, and because of that thrust maybe in this direction for the arch, but this is a series of arch, it will create a stress or that kind of a path will going to create. So, now what are the structural advantage of the shell? Due to its curved profile, curvilinear profile, it treats as it's very natural and it is very stable and strong. It will give you a wonderful long span application, as I discussed that it is almost every portion except some few areas is under compressive stress. So, you can easily use the concrete as a material and you can use it as a long span application, and it is having a better strength to the material consumption ratio, because as you know any kind of brittle material can be act as a very good in the compressive cases or the compressive stress areas, and as the shell is experiencing most of the times compressive stress, the better strength to material consumption ratio can be achieved. The reinforced concrete shell can be widely used and it can be efficiently used as a shell because it can cast it monolithically at a time. The curved profile of the shell will definitely impart better aesthetics look. You can have different type of profile, different type of kind of a the looks in the building, and we will see in this end of this particular lecture and also in the next lecture that how the the master architects that use shell in their different building in a wonderful ways. And typically the circular shells can be precast. You can use the precast circular shell, and that can be used for any purpose of the ready-made housing or those kind of a scenario, where that can be taken into account for construction of building muscle house kind of buildings or so. Now, let us go for some classification of the shell. In the classification of the shell, before we start the classification of the shell, let us discuss the Gaussian curvature. Gaussian curvature is defined as it is a differential geometrical comes in the differential geometry, and suppose a particular surface has two curvature, one in this direction and one is this direction. Suppose a dome or something like that, it has a two curvature, and the two curvature are having some value, curvature value. The curvature value is always going to be the 1 upon the radius of that particular curvature, and the multiplication of this two curvature of that particular two curvature at any point is called as a Gaussian curvature or the Gaussian curvature K, capital K, of that particular point. So, by virtue of value of this K 1 and K 2, K 1 and K 2 are the two curvature of at a certain point because of the two directional curve profile. So, what happened is that because of that particular these two values of K 1 and K 2, the Gaussian curvature, this capital K, can of 0 or it can be of negative or it can be of positive. So, if both the principal curvature, that is K 1 and K 2 is the same sign, it will give you a product as a 0, because K 1 is also has some value and positive value, K 2 is also having some value, positive value. So, that means this is going to be 0. So, suppose simply a kind of like a sphere, a dome can have a R and R in other side, perfect dome can R and R. So, that means their curvature is 1 upon R and another curvature is also 1 upon R. The multiplication of that is 1 upon R square, which is a positive number, and that is positive, and Gaussian curve is positive, the curvature is positive. If a principal curvature of one and other has different sign, suppose one curvature in this way and another curvature in this way, some other way, I mean the opposite way. So, that means suppose something like one is like this and one is like that. So, it has a curvature in this, it has a curvature in this, which are in both opposite in direction, and then it can be give a kind of a negative value of the multiplication value, or the Gaussian curvature is going to be negative, which is hyperbolic, which is a saddle kind of a point, which are kind of a negative kind of a thing will come. So, the Gaussian curvature can be negative also. Sometimes Gaussian curvature can be 0 also, Why 0? Because if either K 1 and K 2 any one is 0, then it can be 0, because suppose one side is flat, suppose it is a barrel vault kind of a thing, cylindrical vault kind of a thing, it has one curvature R and another curvature is all straight lines. So, it is a 0. So, the K 1 is some values, K 2 is 0. So, K is 0. So, Gaussian curvature is 0, and it is called as a parabolic point or so. So, that way we can have the three type of Gaussian curvature, and from that Gaussian curvature let us see the further slides. So, classification of the shell, what we are going to have is that. So, let us consider that one as the first classification with the curvature point of view, number of curvature point of view. Single curvature shells, where the shell is having only one directional curvature and another kind of direction is linear, there is no curvature at all. And those curvatures are the elliptical, circular and parabolic kind of a thing, and it can be a developable kind of a surface. And the another type of classification or other broad classification is a double curvature shell, where we have the two curvature. Dome is example, perfect example of the double curvature kind of a shell. So, it has a curve in both the axis, okay. And then if it is a both the axis, it is non-developable. You cannot develop by cutting off the pieces of the kind of the paper or so, it cannot be developed. So, from that developable and non-developable point of view, it is a single curvature or the double curvature also. Now, we will just see that in this case, in case of a single curvature, as other curvature is linear, the Gaussian curvature is K is equal to 0. Whereas, in second case, when it is a double curvature, it has both the values of k1 and k2 exist, that is the two curvature in two different directions exist, and as now it will be either positive number or negative number because of the or by virtue of the sign of k1 and k2. Well, if both are positive, yes, k is positive, and both are negative, sorry, both are, one is positive and one is negative, then it is a negative. So, we can further classify this curvature, double curvature shell into two types, one k is positive and one k is negative. We will see in the next slide how can I going to classify those. We can classify this as I told that if it is positive, Gaussian curvature is positive, that means it has a center of curvature in the same side, then it is called synclastic kind of a cell. That means, both the curvature are in same side of the shell, and if it is negative, the Gaussian curvature is negative, that means from the center of curvature is opposite side of a shell. Suppose something like a saddle kind of a point. So, one has the curvature in this way, the center of curvature in this side, another is in upper side, other side of the shell. So, if one side is positive, another side is negative. So, finally, the product will be negative, opposite side product will be negative, and this is called anticlastic cell. So, synclastic and the anticlastic cell is actually going to derive from this double curvature shell, the typical classification of the double curvature shell, by virtue of whether the both the direction of the shell, the center of the curvature is in the same side or the center of curvature in the opposite side. Let us see some kind of example. The barrel vault, if I say it is a single curvature cell. Why? This has a single curvature. So, it has a curvature in this, it is a center over here. So, this is the radius of curvature r. Other side, this is the, if this is the x, this is the y, all are straight, no curvature, you see, no curvature. So, the r equal to infinity, and then the 1 upon r, which is curvature, which is k equal to 0, right. So, the Gaussian value is 0, it has some value 1 upon r, the k 2 and k 1 is equal to your 0. So, these are the kind of a shell barrel vault, which is a single curvature kind of a thing. Synclastic, what is synclastic? Synclastic positive, both are positive. So, a kind of a dome or a kind of a vault like this. So, it has curvature here also in x, suppose this is x, this is y. So, this is having a curvature also, this is having curvature also, but both the curvature having their center lie in the same side of the shell, this downward side. So, if had some value of k 1, this has some value of k 2, both are same side, both are having some value, both are having positive value or same sign. So, it is a positive and it is a synclastic kind of shell. So, this is another example of the synclastic kind of shell. See the shell, it has both the axis, if you say this axis, this is and this is, two are the curvature or the center of curvature in the same side. But now, how the anticlastic shell is looking like? Anticlastic shell is like that. Suppose you have this point. So, this is your y axis, this is your x axis, and one curvature is that, this is the curvature, but this curvature is this way. So, the center of curvature is here. So, this is center, this is center, one is this side downward, one is upward. So, this value if it is positive, this value is will be negative, and the product will be going to be negative. So, k value is negative. So, this is the anticlastic cell. So, anticlastic cell is this, where you see this is the curvature and this is kind of a wavy kind of a pattern. So, there are different curvature, one from here and one from this side. So, this product will be going to be negative, and this is the anticlastic cell. A conoid is always going to be a anticlastic, because this has a curvature like that and this is going to be flat in this way. So, again a curvature and flat in this way. So, though both the curvature of one, if you say this is from here, another will be from this side. So, this will going to be product of the curvature will be negative. So, anticlastic shell. Now, we can also find out, or we can have some other kind of a classification also, or the anticlastic and the synclastic shell can be also thought of in different way. It can be come down from two different the definitions of cyanoform and antiform. Those are the definition always going to give by the geologist to see and to see the profile of the earth and the rocks and the earth and all those kind of thing. It is very simple. Any convex downward fold is called the cyanoform, and any convex upward fold is called the antiform. So, any kind of a basin is called the cyanoform, and any kind of dome is called the antiform. So, antiform may have two synclastic also application and the anticlastic application. See how? See, this is a curve in x direction, this is y direction, this is also a curve. Because of these two are the curve, the radius inside, I mean same side this way, it is synclastic. And why it is antiform? Because this and this creates a kind of a the dome kind of a thing, a heap kind of a thing. So, it is a dome kind of a thing. Similarly, a anticlastic, this is and this is, so this is the radius in this way, this radius, the x axis radius in this way. So, it is anticlastic. But because of the nature of this, it can be create a kind of a saddle point, but it can be a kind of this kind of a profile which can create a dome kind of a nature over here, which can create a the anticlastic antiform kind of a thing. Whereas, the cyanoform can be also created like that. The anticlastic, this is anticlastic because this and this are of in two ways, which is a saddle or the basin kind of a thing over here. This is a dome, this is a basin, and also the synclastic, this is synclastic because this is same like that, and both are give you kind of a basin kind of a thing. So, this is a so the anticlastic and synclastic can have a cyanoform or maybe the antiform kind of a situations also. Now, let us see the how the other type of classification can be done of this particular shell. The shell can be classified as in the way like the surface revolutions and the surface translations also. The surface revolution are, you can have a generator and you can have some kind of a other a generator, and if you have a kind of a the axis of rotation, and if you rotate this, you will get a cone. So, instead of that, so suppose if you have a axis of rotation, and if you have a generator like a half circle, and if you rotate that half circle, you will get a dome, right. So, any means, by any means, if you can do some rotation of a kind of a generator, and if you can through that rotation, revolution, surface revolution, you can get a kind of a surface that is come under the domain of the surface revolution. Dome can be created, I told you cone can be created, the elliptoid can be created. You can, instead of this a circular you can have half ellipse can be also rotated about its one axis, it can be ellipsoid, or you can have the paraboloid. You can have a parabola, this is a parabola, and it is actually circulate about this axis, the rotation axis is that. This is also a parabola, and this is rotating about this axis, this can be ellipse, half ellipse, and it is rotating in about this axis. So, you will get a kind of a different kind of surfaces, and those if you now cut it. So, the top part can be act as a kind of a surface or the shell of elliptoid cell half. This can be also act as a kind of a suppose tensile with some you can have some kind of a shell also. So, like that you can invert that one, you can have the inverted kind of a thing and this kind of a support system. So, just half portion and you can just rotate by that, and you can use that as a structural support or that kind of a roof system as a shell. Now, what is the surface translation and the ruled surface? Surface translation on the ruled surface is that instead of the rotation, if you just translate a particular surface with some line or some curved line, you can create another surface. Elliptic paraboloid, what happened is that this is a parabola which is in the x axis, and in the y axis there is a line or a rail which is ellipse. This is ellipse, this is a parabola, suppose. And now, if you translate that parabola over the ellipse track, side track, the parabolic profile line runs over the elliptic edge line. This is the elliptic edge line. You will get a surface which is called elliptic paraboloid. Similarly, we can have a cylindrical paraboloid. What happened? This is paraboloid. So, this is parabola in x axis. In y axis, it is straight line. Y axis it is straight line. Now, if you run that parabola over that straight line, the surface is generated is called the cylindrical paraboloid. Even you can go for the hyperabolic paraboloid. X axis same parabola, but in the y axis a parabolic profile run over the hyperabolic edge. This is a hyperabolic edge. So, it is run like this, goes down and again goes up. So, you will create a kind of a saddle kind of a surface. So, you will create a hyperabolic paraboloid. So, here you see again it is a ruled surface or the surface translation. This can be classified as earlier. So, this is having both the curvature in the same direction. This is synclastic. This is having, this is not a synclastic, this is a simply one sided kind of a thing, that is the single curvature kind of a thing. The k value is 0 over here, this is k value is positive over here. This having a kind of a curvature in the opposite direction. So, k is negative. So, as it is negative, it is anticlastic. So, like that we can see. Also, you can have some kind of a ruled surface kind of a thing. So, what happened here? I have 4 such points, and over that a surface has been created by the ruled, by the some kind of the this kind of mesh can be arranged, or a particular line which is a inclined line can be rotate about the particular axis of rotation with maintaining the corner or the alignment or so. So, that can be created a hyperaboloid, and this is going to be used for, you have seen in the very beginning of my lecture that the nuclear reactor we can use that hyperaboloid. It is an enormous advantage to take care of the load also. So, those are the ruled surface, these are the example of the ruled surface, the earlier was the surface translations also. So, we have some of the classical architectural things that Milo, who has used the barrel vault, you see this barrel vault can be used in his roof. The second one is a kind of a hyperaboloid. Hyperaboloid has a roof structure, is a valley and the top ribs, side ribs or so. It is a octagonal kind of a plan has been taken into account for that. It is also a kind of a paraboloid, and also there are some kind of a shopping center has been created by virtue of some kind of a dome. This is a dome, and there are some diagonal bracings which can be taken by the action of the arch, the thrust action of the arch, and it create a segmental arch in the each and every position, I mean each and every portion of the dome, and this kind of a translation dome can be created, and he has created actually and created by that, and those are almost 40 feet by 40 feet square, this particular dimension 185 feet by 185 feet of the particular area can be supported by the small tripod in that, the octagonal kind of a thing. This is also a small, but it can be act as a large span structure also for this thing. So, and this is another hanger Milo has created. This has a supporting the embankment, and there are two ribs, one is the end ribs and there is central ribs which has actually I mean the discharge are supported by this particular abutment, and this is a kind of a hanger is been created by the perfect profile of the shell. So, I have taken the references this some of the references, and what I have discussed is the shell is a two dimensional derivative of an arch, and it has a membrane stress, it has a orthogonal directional stresses are there, which it can experience throughout its surface, and shell structure can be classified based on the curvature and sometimes also from the surface revolutions or the surface translation point of view. Thank you very much.